Hey guys, welcome back to another exciting Dayland Bio video. Today we are going to start Unit 15, getting close to the end here. Super excited about that. But our first couple of activities that we are going to focus on right now are focusing on electrolytes, acids, and bases. So a lot of this will be review, but some of it will be new material. We need to be able to understand how we categorize chemicals into certain subcategories, and a couple of these would include things like electrolytes, acids, and bases. And these are categorized not only based on their chemical properties, but based on how the chemicals are actually built themselves. So I'm super excited. Let's go ahead and move on. But first, before we start this, today's video is brought to you by Diet Coke. Yes, Diet Coke. All the great taste, less calories. Diet Coke. Very refreshing. You notice I moved up in the world from Big K to Diet Coke. So sponsorship, getting a little bit more there, you know what I'm saying? What are our goals for this video? You should be able to explain and identify electrolytes and non-electrolytes, including acids and bases. You should be able to characterize compounds into acids and bases and differentiate between strong, weak acids and bases. So a lot of this is just categorizing things into electrolytes, non-electrolytes, acids, bases, strong and weak. So if we take a look at some of our vocabulary terms for this particular video, we have quite a few here. So we're going to focus on electrolytes and non-electrolytes, acids, bases, neutral, the concept of dissociation, strong and weak electrolytes, strong acids, strong bases, weak bases, monoprotic, diprotic, triprotic acids, neutralization reactions, and Bronsted-Lowry definition of acid and base. So it's in our nature as humans to want to categorize things. It just makes things easier for us to really remember them and be able to understand them if we categorize them. It's just a fact of human nature. And a long time ago, early chemists worked to categorize chemicals, and one such way is through acids and bases. Now, before they actually knew any of the chemicals and their formulas, acids were things that were simply sour. They turned litmus paper red. You've seen litmus paper before. It's this little piece of paper, you dip it, and it either turns red or blue. If it turns red, it's an acid. If it turns blue, it's a base. An acid actually eats metals to give hydrogen gas. So this is one way that they indicated if they had an acid present. Bases, on the other hand, are bitter tasting. It turns litmus paper blue and they feel very slippery. So bases would be things like soaps, cleaners, detergents, bleach, stuff like that. If there were no signs of this, it meant that it was neutral, that it was neither an acid nor a base. And you probably know that the most common neutral substance that's found on planet Earth is water. So let's take a step back and look at another classification scheme in terms of electrolytes and non-electrolytes. Electrolytes are substances that conduct electricity when you dissolve them in water, and non-electrolytes do not conduct electricity. It kind of makes sense because it has the word electro in it, so it makes it easy to figure out. Now, pure water, while it does have a little bit of conduction of electricity, is actually a non-electrolyte, okay, especially for chemical purposes. Electrolytes dissociate into their ions when you put them in water. So this has to be an ionic compound or an acid, which we'll find out later, because those are the only things that dissociate when you put them in water. Look on the right here, we've got dissolved ions, NaCl. When I put NaCl in water, you know it dissociates into Na plus and Cl minus ions. That is an indication that it is an electrolyte and will conduct electricity. We saw some of this when we looked at our voltaic cell material in our electrochemistry unit. If I take sugar and put it into water, it doesn't dissociate, it doesn't break apart into its individual ions, it just stays sugar. And since it has no ions, it does not conduct electricity and therefore is a non-electrolyte. So how would we classify these things? Electrolytes are going to be water-soluble ionic compounds. Basically, that means that they're ionic compounds, which is a metal plus nonmetal. You know that already. And water-soluble just means that they're not insoluble on your solubility chart. Acids and bases are included in this as well. Remember H and OH. Acids start with an H, and bases, for at least now, end in OH. All right? These dissociate as well when you put them into water and therefore are considered electrolytes. Non-electrolytes would be pure covalent compounds, so two nonmetals that are put together that's not an acid or base. Be careful because acids and bases, particularly acids, do look like non-electrolytes. But remember, if it starts with that hydrogen, you know it's an acid and you know it's an electrolyte. So our first goal here is to identify the following as electrolytes or non-electrolytes. Let's keep in mind that electrolytes have to be ionic or acid/base. Okay, and non-electrolytes are covalent. Okay, so let's take a look. CO2. So it's not an acid or a base because it doesn't start with an H or end with an OH. Is it metal plus nonmetal or two nonmetals? You see it's two nonmetals, so it's covalent, so this is a non-electrolyte. HCl, you should know hydrochloric acid by now. Acids are electrolytes. NaOH, again, that is a base because it ends in OH. So this is an electrolyte. CH4, non-electrolyte. Okay, not ionic and is neither an acid nor a base because it doesn't start with a hydrogen or end with an OH. H2SO4, you know, is sulfuric acid, and you know that acids are electrolytes. Okay, so pretty straightforward on how to do that. Just make sure that you remember the rules on how to identify and differentiate between electrolytes and non-electrolytes. Let's move on. So here's some difficulty with some material with electrolytes. Some electrolytes break apart more than others, and it's important that we know that because that allows us to differentiate between strong electrolytes and weak ones. Let's look at HCl as a great example of this. HCl, when you put it into water, 100% of it will break down into H plus and Cl minus. Now, technically H plus doesn't exist. It actually bonds with H2O to make H3O plus, but just using H illustrates my example here. Because 100% of it breaks apart, it is considered a strong electrolyte. Because every single HCl molecule, when you put it into water, breaks apart into H and Cl, it is considered a strong electrolyte. That is the same thing with something like NaCl. You're going to get 100% of it to break apart into Na plus and Cl minus, and therefore is a strong electrolyte. Now notice the difference in this example here. We have HF. And notice that it is at equilibrium, meaning that not everything is converted to product. Some of it is converted to product, but some of it is not. Roughly only about 3% of the ions actually become a product here. This is considered a weak electrolyte as it only partially dissociates in water. So when I take HF and I put it into water, let's say I had 100 molecules of it, only 3 of them are going to dissociate into solution. So this makes this a weak electrolyte. Now, what are some ways that we can determine the strength of an electrolyte? That is, whether it is strong or weak. Well, one thing we can do is look at the K value that we talked about in the previous unit. You know that if K is greater than 1, it favors production of products, right? And if it favors production of products, like in the reaction here, we get more dissociation. So look at the table on the right-hand side here. Hydrochloric acid has a very large Ka value, 1.3 times 10 to the 6th. So we can say that it is a strong electrolyte because most of it's going to dissociate. Same with sulfuric acid and same with nitric acid. But if I look at the acids below that, oxalic, chromic, phosphoric, most of those have equilibrium that lies to the left, meaning that favors the production of the reactants more than the products. Because remember, a K value that is less than 1 favors our reactant production versus our product. So as a result, we can look at the value for K to determine if it is strong or weak. If K is typically greater than 1, we can consider it a strong electrolyte. If K is less than 1, we can consider it a weak electrolyte. So let's combine the previous two concepts that we've talked about. Acids are anything that put H into solution when dissolved. So we can differentiate these into strong and weak acids. Strong acids, much like strong electrolytes, are ones that completely dissociate when you put them into solution. Weak acids only dissociate partially. So it's really important to know your strong acids, and I would actually commit these to memory. There are 6 strong acids that I want to make sure that you know. HCl, H2SO4, HNO3, HBr, HI, and HClO4. Those are going to be your 6 strong acids that you are going to need to know. And it makes it really easy because if I know those 6 are strong, all the rest are going to be weak. Some acids are capable of producing more than one H3O plus ion per molecule. These are known as polyprotic acids, and that makes sense because poly means more than one, and protic refers to proton, which would be a hydrogen. Acids that only give 1 are monoprotic, 2 are diprotic, and 3 are triprotic. But be very careful here. The number of hydrogens does not correlate with the strength of the acid. The only acids that are strong are the previous 6 that we just discussed. So take a look at the example here. Sulfuric acid, when it loses that first proton, has a very large Ka value. And even when it loses the second one, it's still relatively large. But if I go down and look at phosphoric acid, I notice that it has a very, very low value for K. The K value is less than 1 for phosphoric acid, even though it has more hydrogen with it. Phosphoric acid is a weak acid because its Ka value is less than 1. But notice perchloric acid, which we talked about previously, it's a monoprotic acid and it's a strong acid. And you can see that in the K value being significantly greater than 1. Let's talk a little bit about bases. Bases react with acids to produce some ionic salt and water. Keep in mind, acid plus base always yields salt plus water. Your strong bases are group 1 and group 2 hydroxides. So group 1 and group 2 are your alkali metals and your alkali earth metals on the periodic table. When they are combined with a hydroxide anion, they are a strong base. These are the only strong bases you will encounter. All of the rest of them are weak. So these strong bases completely dissociate when you place them into water. Lithium hydroxide, for example, breaks down into lithium ions and hydroxide ions, and as a result is a strong base because it does so 100%. So let's redefine our definition of acid and base. Our previous definition didn't encompass all acids and bases. It includes a lot of them, but not all of them. So Bronsted-Lowry came up with a new idea on how we can identify acids and bases. Acids donate a proton, hydrogen, and Bronsted-Lowry bases accept them. The acid definition doesn't really change much, but bases no longer have to have OH. So when we look at an equation to determine if something is an acid or base, we have to look at both our reactants and our products. Let's take a look at the example on the right. H2O becomes OH. That H in H2O goes on F. So H2O donates an H where F minus gains that H. If you donated that proton, you are an acid, and water did just that. Fluorine accepted the proton, or accepted the hydrogen, and therefore is your base. So it's relatively easy to determine acid and base in a reaction. You just have to look for what donates the hydrogen, and then what accepts it. Let's go ahead and determine the acid and base in the following reactions. Remember that acids donate H, and bases accept H. So if I look at the two species over here, which one donates and which one accepts? If you look, it appears that this H here is donated to NH2 to create NH3. So because this donated, this is our acid, and this is our base. In the following example, we can see something very similar. NH3 here donates a hydrogen to pH3, which makes it pH4, and NH3 goes to NH2 minus. So therefore, this is your acid, and this is your base. Okay? So it's relatively easy to look at a problem and be able to figure those things out. Let's move on. So weak acids and bases tend to be a bit more difficult to identify than strong. But again, if we look at the K value and we've memorized our acids, our strong acids and our strong bases, then this becomes very easy to do. If you're given K values, if it's less than 1, it's probably weak. The further less than 1 an acid or base is, the weaker it is. And the larger the number than 1, the greater and strength is in the acid or the base. Weak bases often have nitrogen with the lone pair of electrons on them. For example, NH3, or this example here. This example here, because it has those lone pair on it that are negative, tends to attract hydrogen, which has a positive charge. So just a couple of ways to look at weak acids and weak bases in order to be able to determine what they are. But again, key thing here, make sure you memorize those strong acids and strong bases. That's all I have for you today. Hopefully you had a good time with this video. I know I had a good time going through it. My voice for some reason sounds a little bit different and I have less verbal stumbles as I go through these videos. Maybe I'm finally 300 videos later starting to get good at this. Who knows? I wish you guys a great day. Stay safe and we will talk to you later. Bye-bye.